Okay, let's get into actually what we want to talk about today, which is something called, it's one of my favorite topics. In graph theory, it's the area of graph coloring. So let C be a set of colors. Okay, so I'm just giving you a definition right now. So a proper coloring, so what's a coloring of a graph? I call it we're going to call it a proper coloring, but if I use the word coloring, I usually mean proper coloring. So maybe I'll put this into parentheses here. So usually when I say coloring, we're always going to talk about a proper coloring. So proper coloring of G is a function f from the vertex set of G to the set of colors C. Okay, so C could be any set of colors. It doesn't, to be honest, C doesn't have to actually be colors, right? It doesn't have to be red, blue, green, whatever. It's just a set. Okay, so C is just a set, any set. So it could be the numbers 1, 2, 3, 4, 5, or whatever. Okay, so proper coloring is a function from the vertices of G to C such that adjacent vertices get different colors. So f of u is not equal to f of v whenever uv is an edge of G. So in other words, every edge, if I look at an edge, it has to have different colors on the endpoints. Okay. So any questions about the definition? Because this is quite important for today. Okay. If not, then, so in other words, just to kind of say the same thing in a different way, a proper coloring assigns each vertex to a color such that adjacent vertices have different colors. So this sort of thing is not proper. So if I have two vertices which are joined with an edge and they both are colored blue, or whatever this color is, kind of a bluey gray, then that's not proper because I've got adjacent vertices that have the same color. But this is, down in this corner, this is an example of a proper coloring because if you look at every edge, you'll see that the two vertices of that edge get different colors. So this one is red and green, that edge is blue and red, and you'll never see a blue joined to a blue or a red joined to a red or a green joined to a green. So that's what a proper coloring is. Okay, any questions about the definition? Okay, so the kind of main focus in coloring, graph coloring, is to determine the optimum number of colors. So you want to color a graph with the smallest possible number of colors. So kind of in this direction, we make it a few definitions. So for each, so if k is a natural number, a graph G is said to be k colorable if there exists a proper coloring of G using a set of k colors. So just kind of to make a sort of generic choice here, I'm going to, usually I'll use the colors 1 up to k, but the set of colors doesn't really matter, right? If I have, the colors red, blue, and green, or the colors 1, 2, 3, or A, B, C, the name of the color doesn't matter. But so for the sake of this definition, I'm just using the colors 1 up to k. But yeah, it could be replaced with any set of size k. And then the chromatic number of G is the minimum k such that G is k colorable. So like I said, we're interested in kind of optimizing the number of colors. So finding the smallest k such that G is k colorable. So is this definition clear? Are these definitions clear? I guess I'll assume the silence means that it's clear. But yeah, so, proper coloring, you have vertices, adjacent pairs of vertices have different colors, and our goal is to find the smallest number of colors such that you can do that. Okay, so that's the chromatic number. Just to make it clear, so when you want to determine the chromatic number, or in other words, if I want to show that I have a graph and I want to show that chi of G is k. So by the way, the chromatic number, so chi is the chromatic number. It's pronounced, so this Greek letter is pronounced chi. Well, that's at least how it's spelled. So chi. Right, so if I want to determine the chromatic number of a graph, I need to prove two things, right? Just to make it clear, I need to show that the graph G has a proper coloring with k colors. So I need to show that G has a proper coloring using K colors. Okay, and if G has a proper coloring with K colors, then that proves the upper bound, right? That'll prove that chi of G is at most K, because, you know, it has a coloring with K colors, and it might have a coloring with K minus 1 colors, but it's not clear, right? And then you need to show that G has a proper color, or does not have a proper coloring using K minus 1 colors. And this is usually the harder part, okay? And this proves then that the chromatic number is at least K, because it can't be less than K. If it was less than K, I would have a proper coloring using K minus 1 colors. Okay, so when you're given a question to determine the chromatic number of a graph, don't just show me a coloring, right? Because that's not good enough, because you have to show that there doesn't exist a coloring that uses fewer colors. Is this clear? Okay, so let's do a poll. See if we understand this. What is the chromatic number of this graph? So I'm giving you lots of options here. 1, 2, 3, 4, 5, 6, 7, 42, or I don't know. So what's the minimum number of colors such that you can color the vertices of this graph and different vertices get different colors? So remember, it's the min, K, such that you can color the vertices and different vertices, or sorry, not different, sorry, adjacent vertices get different colors, right? Just to remind you what I'm asking for. There seems to be, so not everyone has voted yet. There seems to be some consensus, like different, or two different answers, which are kind of in the lead. Well, so I think sometimes it's good to do these things by process of elimination a little bit. So why is the answer not 1? Or sorry, could the chromatic number be 1? And if not, then why not? So anyone want to answer that in the chat? Why is the chromatic number not 1? This is maybe the most basic question. Anyone have a reason for that? Yeah, so this is perhaps, a little bit almost too simple, but like if I just take two vertices, like this one, right? Suppose it gets red without loss of generality. And then I look at a neighbor of that vertex. Well, it has to get something different than red. So therefore, that proves that the chromatic number of G is at least 2, because there can't be, if I give everybody the same color, obviously I've got adjacent pairs that have different color, or sorry, the same color. Could it be 2? So that's kind of the next natural place to try. Is it 2? And let's just try to color it, right? So suppose if I'm coloring with two colors, red and blue, since this one's blue, its neighbors have to be red, right? Because I'm only using two different colors. So the neighbors, I make all the neighbors of the blue one red because I have to. They have to be different colors. And then I can make these ones blue, right? Because all of their neighbors are red. And actually, if you look at it, this is a coloring. It's a proper coloring, because if you look at the edges, all of the edges have different colors. So the existence of this coloring proves that the chromatic number is at most 2. Okay, so therefore, the chromatic number of G for this graph G is equal to 2. Okay, so some people seem to put 3. Some people put 6, which maybe 6 is the number of vertices. So if we wanted all the vertices to have a different color, the answer would be 6. But we don't want all vertices to have a different color. Okay, just the adjacent pairs. That's our only restriction. So thanks to anyone who answered this. I think the majority got the right answer. A few people said 3, but yeah. Is it clear? Any questions about this example? Okay, so just to clarify, if we wanted to show the answer was 3, we have to show that there's no coloring with two colors, but this example shows that there is a coloring with two colors, a proper coloring. Okay, so graphs like the one I showed you on the previous slide, so graphs that have a coloring with two colors, are quite special, okay? So that's what we're going to kind of focus on in the next few slides. So what I'm going to prove is that a graph, G, has a coloring with two colors, or in other words, chi of G is at most 2, if and only if G has no odd cycles. Okay, so this is I think it's a kind of interesting theorem which kind of classifies the graphs that you can color with two colors. And like I said, this is going to be kind of special in the sense that if you have 3 colors or 4 colors, there's not going to be you're not going to have a similar kind of simple characterization. Okay, so is it clear what I'm saying in this theorem? Okay, so up here I've just restated the theorem again. So this is just chi of G is at most 2. We want to prove that this is if and only if G has no odd cycles. So let's do one direction. So let's do the forward direction. So if chi is at most 2, then G has no odd cycles. So we're going to do this by contrapositive. So we're doing this direction here by contrapositive. So we're saying, assume that G does have an odd cycle, and now we have to prove that the chromatic number of G is not less than or equal to 2. So can anyone see what's going to happen here? So I take an odd cycle V1, V2 up to V2k plus 1. For example, let's say a cycle of length 5. So why can't I color G with two colors? And it's going to obviously have something to do with the odd cycle. And let's just think about maybe the 5 cycle. Any thoughts? So why can't I color this properly with two colors? Well, yeah, so that's actually kind of, so there's something in the chat, if you use two colors, there's going to be two adjacent vertices with the same color. That's kind of like the definition of why it's not, it's kind of by definition. But yeah, that is the reason. I mean, so how do we see this using the odd cycle? So if I take, let's say I start somewhere, I give this one red, like without loss of generality. Like, so my two colors, by the way, are red and blue. Okay. Without loss of generality, I can give that vertex red. Okay. Because, or I give it blue and then I just change red to blue in everything I say. Okay. So the first one's red, let's say. Second one has to be blue because there's only two colors. I don't have another choice. It's adjacent to a red one already, so it can't be red. There's not a third choice of color, right? So if you're not red, then you must be blue. So the second vertex has to be blue, and then by the same argument, the third vertex has to be red, the fourth vertex has to be blue, and now I run into my problem that the fifth vertex, it kind of has to be red, because it has a blue neighbor, but that gives us a contradiction here because I have a red joined to a red. Okay, so it's because of the oddness of this cycle. The fact that the cycle has an odd number of vertices, that causes the problem. So just to be more formal here, so if V1 is red, then that implies that V2 is blue. So if the first vertex of the cycle is red, the next one is blue, which implies V3 is red, which implies, V4 is blue, right? And so on. And kind of inductively, if some odd, like V2i minus 1 is red, like implies that V2i is blue. And V2i is blue implies that V2i plus 1 is red. Okay, so what happens here, as you can see, is that all of the the vertices with odd index are red and all the even ones are blue. So Vi is red, or let's call it Vj, if j is odd, and Vj is blue if j is even, right? I'm just repeating this argument we had on the 5 cycle, but in more generality, right? So the first one is red, the second one is blue, third is red, fourth is blue. So even numbers are red, odd numbers are blue, but we get a contradiction because V2k plus 1 is adjacent to V1, and both of them are red. So contradiction, right? So if you have an odd cycle, then you cannot color the graph with two colors. So that proves this direction, this direction of the theorem by like contrapositive. So I assume that the right-hand side is false, and I get that the left-hand side is false. Any questions about that part of the proof? Okay, so let's try to prove the other direction. It's a little bit, I mean, it's not much harder, but a little bit, you have to do a bit more thinking, I think. So again, at the top, I've restated the theorem. So let's, so what I'm proving now is I'm assuming G has no odd cycles, and I'm going to prove that it has a proper coloring with just two colors, okay? And the two colors are going to be red and blue. So I just pick a vertex V, okay? Pick any vertex V, color it red, okay? So we have to start somewhere. And without loss of generality, I can just start by giving some vertex red. Now, if you think about it, what color are the neighbors? What color do the neighbors of V have to be? So I'll ask this to the audience. So what colors do all of the neighbors of V have to be? What color, I guess? Right. So the answer is blue, as was mentioned in the chat. So anything at like distance 1 from V has to be blue. If I take something at distance 2, so here I'm defining, so just to be kind of formally, I define, given a vertex U, I define the distance from V to U to be the length of the shortest path from V to U. Okay. Now, there's one annoying thing that maybe the graph is disconnected. So maybe there's some vertices which are in different components, and so there's no path from V to U. But I just say that, okay, for those vertices, the distance is infinity. So now, if I look at a vertex at distance 2 from V, what color does it have to be? And hopefully it's fairly clear that it's red, right? Because, yeah, it's got to be red. Because if it's at distance 2 from V, then if I kind of trace it backwards, I take a path from that vertex back to V, it has length 2. Well, the shortest one has length 2. So this guy must be adjacent to a vertex that's blue, so it must be red. And so on and so forth. And so it's kind of clear how to construct a coloring. Basically, we have to, what we do is we take any vertex which is in the same component of V, and we give it blue if it's at odd distance from V, and we give it red if the distance is even, if the distance from V is even. And then if the graph is disconnected, we can just repeat this on every component. So on every component, we just pick a special vertex and we define the coloring based on the distance from that vertex. Is that clear? So this is what I'm saying here, color every component in a similar way. Okay, so I kind of already illustrated this, but the idea is, okay, I start with V, color its neighbors blue because you have to, because V is red. Look at the vertices at higher distance 2, let's say, color them red, and so on. Distance 3, you color them blue. Distance 4, you color them red, and so on and so forth. Right. Now, is this a proper coloring? Is my question. So, well, if this isn't a proper coloring, then there's a pair of vertices, U and W, that get the same color, and they're adjacent. So either U and W are both red, or they're both blue, and there's an edge from U to W. Now, so I want to get a contradiction. So let's suppose that they're both blue, because it's not going to make a difference. So there's an edge between two vertices that are blue, and the shortest path, so I can look at the shortest path from V to U and the shortest path from V to W. So where do I get the contradiction here? So it's kind of written on the slide, but can anyone see why these two vertices being adjacent and both being blue is a contradiction? Can anyone see it? And yeah, it's kind of in the picture, but any thoughts? Yeah, exactly. Basically there's an odd cycle somewhere, right? And that's what we were trying to find. We're trying to show, well, it's again kind of by the contrapositive. We wanted to kind of show that if I can't color with two colors, then there's an odd cycle. But anyway, so we're trying to we assumed that there wasn't an odd cycle. We tried to do this coloring, and what I want to find now is an odd cycle. And you can kind of see that it's going to be, if I take these shortest paths, so at the top I've got the shortest path from U to V in the graph. At the bottom I've got the shortest path from U to W, W to V. These paths are either both even or both odd. Okay, so I've kind of drawn them. They might intersect a few times, but they may not intersect, right? They may just look like this. It depends. They could just be completely disjoint, right? If they were completely disjoint, it might make things actually a bit easier, because if you think about it, here I've got let's say, I've got, say an even number of vertices or an odd number of vertices or whatever. And here I've got the same, even or odd. So I've got, like, let's say the number here is k and the number here is L, right? So the number of vertices in this cycle in total is k plus L plus 3, which if k and L are both odd, then this is odd. If k and L are both even, it's also odd, because an odd plus an odd is an even plus an even is an even plus an odd is an odd. So because k and L are both even or odd. But the same thing actually works in this picture too, because I can follow the path from U towards V. I can just take the first time, and I can follow the path W back to V. I can take the first time that they intersect, okay? And this vertex has a certain color. It's either red or blue. And, no matter what color it is, the kind of number of vertices, the parity, the evenness or oddness of how many vertices you have in these two paths is going to be the same, if you think about it. Okay, so this gives us an odd cycle, which is a contradiction, and that actually completes the proof. So maybe there's some things I'm writing and not saying. Here's the kind of, the explanation here. So if I take the last place where these two paths intersect, then the distances from x to u and x to w are both either even or both odd. That's just because of, this vertex has a certain color, right? It's either blue or red. And then the next vertex on this path would have to be blue, the next would have to be red, and so on and so forth. And these things have the same color. So the number of vertices here, if it's even, it has to be this one has to be even, and if that one's odd, then this one has to be odd. Okay. So hopefully that's fairly clear. So this gives basically a way of recognizing if a graph has chromatic number at most 2. Okay. Are there any questions about anything? So the message here is a graph, it has chromatic number at most 2 if and only if it has no odd cycles. Okay. Or in other words, if and only if so if it has a proper 2 coloring, if and only if there's no odd cycles. Okay. So now I want to give you another perspective on the same concept, because so this is an important kind of terminology for you. So a graph G is bipartite if the vertex set can be partitioned into sets A and B, such that every edge of the graph goes from A to B. So in other words, a bipartite graph looks like this, right? You've got the vertex set is written as A and B, where A and B are disjoint. So this, when I say partitioned, I mean that A union B is equal to the vertex set of G, and that A and B have empty intersection, so they're disjoint. So a bipartite graph looks like this. It's A and B, and every edge goes from A to B. So there's no edges. So no edges, in other words, inside A, and no edges inside B. So as a corollary to the previous theorem, so I want to say that G is bipartite if and only if the chromatic number is at most 2, if and only if G has no odd cycles. So this part of the theorem was what this part of the corollary is what we just proved. This if and only if. So can anyone tell me why this one's true? So G is bipartite if and only if the chromatic number is at most 2. So there's a question actually going back to the previous slide. So yeah, there was something here that was maybe a bit subtle. Here, what I've got written here is that these two paths have to be the same length, that this has to be the same length, and so on. So by the way, I'm not saying these might have different lengths. Okay, so these may not be the same length. Actually, no, they do have to be the same length, I think. The reason why these have to have the same length is because they're the shortest path. So if one was shorter, then I could get so the bottom is supposed to be the shortest way to get from V to W. If the top thing was shorter from this point to that point, I could just follow along here and then walk to W, and it would be faster than taking. So you can't have something shorter than the shortest path. That's the point. Okay, so great. Yeah, so there's an answer to this question here about bipartiteness. So the A and B, well, yeah, the A and B kind of are the colors, right? So if a graph has, so going one direction, like if G is bipartite, it can be partitioned into A and B. The vertices can be partitioned into A and B, so there's no edge inside of A and no edge inside of B. And of course, I could just say, okay, everybody in A gets red. Everybody in B gets blue. And that's going to be a proper two coloring because every edge will have a red endpoint and a blue endpoint. And the other direction, if I have a proper coloring with two colors, so some of the vertices are red, some are blue, I could say, okay, let A be the set of all red vertices and let B be the set of all blue vertices. And that gives me, that shows that G is bipartite. Actually, another bit of terminology here. So we say that the sets A and B, so the pair AB is a bipartition of G. So if G, so what I'm saying, I guess, is if G has a coloring with red and blue, just two colors, a proper coloring, then if I look at the red vertices and the blue vertices, and I let the red ones be A, the blue ones be B, that gives me a bipartition. So therefore, G is bipartite. Okay, so this is just another way of saying the same kind of concept, but it's important for you to know the word bipartite because, yeah, bipartite graphs are very important in graph theory. Okay, so here's a very, I think, an extremely natural question. So here I've told you how can you how can you tell if a graph has chromatic number 2, and the answer is it has chromatic number 2 if and only if it doesn't have an odd cycle, which is kind of it's a nice structural characterization of graphs with chromatic number at most 2, right? It kind of tells you this is the structure. This is why a graph has chromatic number at most 2 or why it doesn't. It's all about odd cycles. And also, by the way, the way that we proved that theorem also gives a really natural way to test whether a graph has a proper 2 coloring, right? Because all you have to do is you start at a vertex, you give it red, you give its neighbors blue, you give their neighbors red, you give their neighbors blue, and if that works, then it works, and you found a proper 2 coloring, and if it fails, it's actually going to show you how to find an odd cycle. Is that clear? Because once you find, if that procedure gives you 2 vertices that are both adjacent and they're both red or both blue, you can kind of trace it back and find an odd cycle. So this gives a kind of natural algorithm for testing if a graph has chromatic number at most 2, or in other words, whether it's bipartite or whatever, or whether it has an odd cycle. Now, personally, I think an extremely natural question is, what about if we want to have a similar understanding about graphs of chromatic number at most 3, right? Can we understand the structure, the underlying structure of a graph with chromatic number at most 3? And the answer is kind of no. I can't give you a deep reason for this right now because, well, it requires understanding. So similar to the topic of Hamiltonian graphs, it requires some kind of background in computational complexity. But what I can say is that algorithmically, it is a hard problem to decide whether a graph has a proper 3 coloring. So in other words, we don't have a good algorithm to do this. And we believe, and when I say we, I mean most of the human race, I guess, believes that there probably doesn't exist a good algorithm to test if a graph has a proper 3 coloring. And so therefore, there also doesn't exist a nice structural understanding of these graphs. And the reason is because the problem, so 3 coloring a graph, or testing if a graph has a 3 coloring, so just a bit of terminology that I won't actually define, but it's good for your mathematical, exposure, I guess, that the problem of deciding if a graph has or doesn't have a proper 3 coloring is an NP-complete problem. So in other words, it's hard. So that's what you should take from this slide. Is what I'm trying to say clear here, or are there any questions about it? So because it's a hard problem, there's no way I can, I could on a test or something give you a graph and try to ask you to find a 3 coloring, but it would have to be like the answer would have to be sort of obvious, or not that hard to work out, because like I can't give you a systematic way to check if a graph has a 3 coloring. I can't do it because there doesn't exist a way of doing it, which is kind of interesting, I think. So this issue of hard problems is interesting. Okay, let's talk about, so it's hard to determine the chromatic number of a graph, okay? But let's kind of think about some restrictions or some properties of a graph which can let us bound the chromatic number. So a clique in a graph G, or some people pronounce this click, but I think I prefer clique. So a clique in a graph G is a set of vertices S, such that UV is an edge for all U and V in S. So it's a set of vertices, let's say, 5 vertices, such that every pair is adjacent. I missed one. There it is. So this is a clique with 5 vertices. And okay, the clique doesn't have to be the whole graph, so there can be other stuff in the graph. But if I kind of focus in on this set of size 5, that's a clique. So here's a easy proposition that if G has a clique with k vertices, then the chromatic number of G is at least k. Can anyone see why this is true? And I hope it's okay for me to ask these kind of questions, which some people may find trivial, but I think I just want to get people thinking, I guess, about these ideas. So why does if G has a clique of size k or k vertices, why does this hold? The chromatic number is at least k. Any thoughts? Oop. Yeah, exactly. That it is that easy. That if I zoom in on the clique, right? Everything in the clique has to get a different color. So all vertices in the clique get a different color, because if they didn't, well, by definition of a clique, so if U and V are in the clique and they get the same color, then there's an edge that goes from U to V, but that would contradict the fact that it's a proper coloring. So therefore, kind of by pigeonhole, if you want to think of it that way, there must be at least k different colors. Because if you think about it, if you think of the colors as being holes and the vertices as being pigeons, the vertices of the clique being pigeons, if I had only k minus 1 colors, then 2 of my vertices of the clique, or 2 of my pigeons, would have to go in the same hole, because there's k pigeons and k minus 1 holes, so they would have to get the same color. Okay. If I ask you to prove this on a test, if you don't write the pigeonhole principle, but you seem to understand why they have to get different colors, that would be good enough. But basically, yeah, so there has to be k different colors, because all the pairs of vertices must have a different color in a clique. Okay, here's a somewhat more interesting proposition, but also fairly easy. So let me give it a couple of definitions first. So capital delta of G. So both of these things are called delta. The one that looks like a triangle is like uppercase or capital delta, and the other one's lowercase. So these are all from the Greek alphabet, right? Uppercase. So remember what the degree is, right? So in a graph, the degree of a vertex is the number of edges that come out of it. So degree here is 3 of that vertex, right? And capital delta we define to be the maximum degree of a vertex in the graph, and little delta, or lowercase delta, we define to be the minimum degree of a vertex in the graph. And I claim that the chromatic number of a graph is always at most capital delta plus 1. So any thoughts about how to prove this? So it's not a super difficult proof, but it's it's a little bit harder than what we just did about cliques. So how would I prove chromatic numbers at most delta plus 1? Any thoughts? Well, okay, so what I'm going to do is I'm going to do it by induction, okay? So the case where the number of vertices is 1 is always, I mean, at least it's usually pretty boring. In this case, it's also boring. So this is the base case, right, of the induction. So, okay, what is delta of G if I have a graph with one vertex? Remember, it's a graph, not a multigraph, so there's no loops, right? So if I have one vertex, I don't have any edges. So delta of G is 0. Chromatic number of G is 1 because to color one vertex, I need one color, but I don't need two colors because there's only one vertex. So in this case, it checks out. In fact, it's equality. So this is the base case, and it's done. So now suppose that the number of vertices in G is at least 2. Okay. Let V be any vertex of G. So what we're going to do is, so we want to use induction. So we need to go to a graph which has a smaller number of vertices and apply the inductive hypothesis. So is it clear what my inductive hypothesis is? Right? Inductive hypothesis is that every smaller graph satisfies the inequality. Okay. So let G prime be the graph G minus V. So here I mean, whenever I write G minus V for some vertex, so this is the graph I get by deleting V and all edges that contain V. Is that clear? So here is a kind of easy, the question, is it at least? So are you asking about this in this proposition, or, sorry, I missed that when it was asked. If you want to clarify what you mean by at least. Chromatic number, or sorry, let's say I look at the maximum degree of G prime. Well, it can't be bigger than the maximum degree of G. Because obviously, if I take a graph and I delete a vertex, like that can't create a vertex of higher degree, right? The degrees actually just go down when I delete a vertex, or they stay the same. So therefore, if I applying the inductive hypothesis, so the inductive hypothesis is just that this inequality is true for all smaller graphs, right? So if I apply the inductive hypothesis to G prime, we get a proper coloring. I'll just say coloring here, but I mean proper, with at most delta of G prime plus 1 colors, which is at most, which is at most delta of G color plus 1 colors. Okay. Now what I'm going to, so imagine, I've got this graph G, I delete a vertex, and then I find a coloring of the remaining graph. Now if you imagine I'm going to put this vertex back into the graph, and we're going to see that when I put it back into the graph, so that's, if you think about all of the other vertices as having a color except for V, right? So everything except for V already has a color because we colored G minus V. Now so what I have to do is I have to give V a color which is different from all of the color of its neighbors, all of the colors of its neighbors. So can anyone tell me why I can do that? So I claim that there exists a color. So I look at the colors of the neighbors of V. Yeah. Oh, I think somebody unmuted. I look at the colors of all the neighbors of V, and I want to give V a color that's different from all of those colors. So why does that exist? And feel free to either unmute or to say in the chat. Yeah, exactly. So the vertex V has the maximum number of neighbors it could possibly have is delta of G. And in the universe, there's at least delta of G plus 1 colors. So there exists a color for V that doesn't appear on the neighborhood of V. Neighborhood, I mean the set of neighbors of V. So choose a color for V that is different from the colors of its neighbors, and that exists because V has only delta neighbors. So it exists or at most, because the degree of v is at most delta of g, right? And the number of colors is delta of g plus 1. Okay, so that completes that proof. Are there any questions about that? Okay, let's I don't know, play around with these. So let's apply these two propositions. So first, let me give you a definition. So for n at least 1, the complete graph Kn is the graph with n vertices such that every pair is adjacent. So remember, we saw this definition of a clique before, right? So in other words, a complete graph is a graph where the whole vertex set is a clique. Remember, a clique, I said, is a set of vertices in a graph that are all pairwise connected with edges. A complete graph is just a graph where the whole thing is just a big clique. So every pair of vertices in the entire graph is adjacent. So, and I call the clique with n vertices Kn. So K1 is just a single vertex, K2 is a single edge, K3 is a triangle, K4 looks like that, K5 looks like this, and so on. By the way, maybe just to practice with, I don't know, counting and these graph theory definitions, maybe quickly, so how many edges does Kn have? So maybe answer in the chat. Maybe I could have maybe made this as a poll, but so the graph Kn, complete graph on n vertices, how many edges does it have? Does anyone know? Can anyone tell from the definition? Not quite. So there's an idea in the chat, n minus 1 factorial, not n minus 1 factorial. Ooh, that's an interesting observation. How did you get that? So n minus, but this is going to be correct. Not for the reason that I wanted it to be, or not the way I wanted you to do it, but that's perfectly fine. So n minus 1 plus n minus 2 plus n minus 3, blah, 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 all the way down to 1. That's correct. I guess you could think of that as like, take one vertex, it has degree n minus 1, delete it, so that removes n minus 1 edges, and then you're left with complete graph with n minus 1 vertices, and then, is that how you got it? Or I don't know. But okay, so that is correct actually, but the way I would have preferred to write it is n choose 2. Okay, but it is also equal to the sum I equals 1 to n minus 1 of I. So that's something we proved back in, like, I don't know, the section on combinatorial proofs or something else. But why is n choose 2 a good answer? Because it's just, so to kind of answer my own question here, so the number of edges in the complete graph on n vertices is n choose 2, because every subset of size 2 of the vertex set is adjacent, right? So like the edges of the complete graph are exactly the sets of size 2. Every set of size 2 is an edge, and every edge gives you a set of size 2. So it's just n choose 2. But yeah, you could have also got this by computing this sum. Okay. All right. So if anyone ever asks you how many edges does the complete graph have, it's n choose 2. So a corollary of the previous two propositions is that the chromatic number of Kn is n. Why? Well, I mean, you don't need to apply any propositions to get this. If you think about it, it's pretty clear, right? Any two vertices have to get a different color because there's edges between them. There's an edge between them. And if I just give everybody a different color, then that is a proper coloring. But also, you could just say, okay, it's at least n because, so this is I mean, it doesn't matter how you prove this, but so Kn has a clique with n vertices. So if I wanted to apply the proposition, and I can say that it's at most the delta of Kn plus 1, which is also n, because in Kn, as was, said in the chat, so related to what was in the chat, every vertex in Kn has degree n minus 1, so the maximum degree is n minus 1. Okay, so the chromatic number is equal to n. Another definition, so let Cn be the cycle graph on n vertices. So it's just the graph where the whole thing is just a cycle. So it's n vertices which are arranged in this kind of cyclic way. So C3, so there's no cycle of length 2 because that doesn't really make sense in a graph. It kind of makes sense in a multigraph, a cycle of length 2, but not in a graph. So C3 is the cycle of length 3, also known as the triangle. C4 is the cycle of length 4, cycle of length 5, and so on. So can anyone tell me, so I want to write down the chromatic number of Cn. Now, it's going to be different if n is even or odd. So can anyone tell me either of these two cases? What is the answer for an even cycle, and what's the answer for an odd cycle, the chromatic number? So what about, whichever one comes to mind. Even cycle, odd cycle. So what if it's even, let's say? What's the chromatic number? And right. So for the even case, the answer is 2. For the odd case, the answer is 3. For the even case, the answer is 2 because if you think about it, an even cycle doesn't contain an odd cycle. So even cycles are bipartite. They have chromatic number at most 2. And clearly, the chromatic number is at least 2 because, if you look at two adjacent vertices, they have to get different colors. So this is because bipartite, or, there's no odd cycle here, and contains an edge. For the odd cycle, the answer is 3 because so the lower bound comes from the fact that, it has an odd cycle. So an odd cycle is an odd cycle. So it's at least 3 because it's odd. It's an odd cycle. And it's at most 3 because it's at most delta of g, or delta of Cn plus 1, which is 3 because the maximum degree is 2. So the upper bound you get is 3. Okay. Let me just, I know the time is up. Let me just quickly mention a cool theorem, which we're not going to prove. It's beyond the scope of this course. But maybe if you take graph theory like Math 423 or something, you may see this theorem. So this is called Brooks's theorem. So remember we showed that every graph has chromatic number at most delta plus 1. What Brooks proved is that this is equality. So the only graphs that have chromatic number delta plus 1 are, so if and only if either G is a complete graph or G is an odd cycle. Okay. And we just proved complete graphs and odd cycles have chromatic number delta plus 1. And what Brooks's theorem says that actually every other graph, like any graph that's not a complete graph or an odd cycle, has chromatic number at most delta. So in other words, every other graph satisfies chi of G at most delta of G. So this is not really a big part of the course because we're not going to prove it, but it's just interesting, I think, for your mathematical education.